We discuss supervised learning, a type of machine learning that is guided by labeled data. Before we introduce supervised learning, let us define machine learning. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. We will use this definition to guide our discussion on supervised learning. This is our outline. We will focus on experience, task, and performance, all in the context of learning. Probably, robot learning is one of the most evident types of machine learning. In this video, a robot has learned how to perform the challenging task of pick and place and sorting. For humans, we take this skill for granted. For machines, this is a very challenging task. This type of robot capability has a huge impact on automating e-commerce distribution centers. Supervised learning is characterized by labeled data. In this slide, we define supervised learning in the context of classification. Experience can be obtained from dataset D-train, made of input xn and label yn, both of which have certain dimensionality. In this case, we assume that xn is a vector rd while yn is a scalar. D-train has n labeled samples. The task is to classify the input by learning a function f or model that correctly predicts the label. Learning is finding the values of parameters or data. Function f can be validated by using ground truth experience d-test with m labeled samples. Before we illustrate learning, we define accuracy on d-test as the performance measure of our classifier. Accuracy is the number of correct prediction divided by the size of the test. Initially, the model does not perform well on the test. It generates many incorrect predictions. While observing the samples from D-train, the model adjusts the parameter to correctly map each input to its label. Theta star represents the set of optimal parameters. After training, the model has improved its performance. From our earlier definition, there is an improvement on the performance of tasks due to experience. We exhibit machine learning. In machine learning, another important performance measure is generalization. The gap between accuracy on D-train and D-test must be as small as possible. A small gap indicates the model will potentially perform well on new unforeseen inputs. In supervised learning, the model experience depends on dataset. We show different datasets. MNIST Dataset is one of the simplest and commonly used datasets in vision. X is 28 by 28 grayscale images of digits 0 to 9. Y is the class label. D-train has 60,000 elements while D-test has 10,000 elements. MNIST is available on Torch Vision. In speech, LJ speech is a common dataset. X is made of speech waveforms while Y is the corresponding text transcript. LJ speech is available on Torch Audio. For sentiment classification, SS2 is commonly used dataset. X is the phrase or sentence while Y is the corresponding sentiment. SS2 is available on Torch Text. The source of experience enables models to perform useful tasks. In machine learning, there are many different tasks. In the following, we describe common ML tasks. Multi-label recognition or classification is a common problem in vision, speech, and other types of data. In recognition, the task is to assign the correct label for a given input. For example, in MNIST digit classification, the goal of the classifier is to assign one of the 10 digits to the given input image. Instead of directly predicting the category in scalar format, the label is predicted using the 1-hat vector format. 1-hat vector is a vector with dimension equal to the number of categories. All values are 0 except at the correct class index. The sum of each row is always equal to 1. During prediction, each element can be interpreted as probability or confidence. This task is also known as multi-class logistic regression. A much simpler classification is binary classification. The task is predicting one of the two possible values. For example, in sentiment classification, a praise could either be positive or negative. Positive is represented by 1, while negative is represented by 0. This task is also known as binary logistic regression. Sequence-to-sequence modeling is a more complex task. In this example, the task is to generate speech waveform given text. This is a challenging problem in speech synthesis or generation. Given a text, it is converted into phoneme sequence or feature or embedding sequence. The model converts the embedding into sequence of WAV samples. A more common task is curve fitting or linear regression. For example, given data points in red, we fit a polynomial in blue as an approximate function. This task is also known as linear regression. Learning has to be quantified. Performance is a measure of learning progress. In the succeeding slides, we enumerate certain measures of learning. For multi-label classification, we use accuracy as a performance measure. We will use arrow up to indicate that we want this value to be as high as possible. The opposite of accuracy is error rate, something that we want to be as low as possible. Accuracy on D-test is the model's number of correct prediction divided by the number of elements in D-test. In ASR, the performance is measured using word error rate. This is equal to the sum of substitution, insertion, and deletion divided by the number of spoken words. Substitution means the replaced word. For example, the word night is replaced by night. Insertion means the added word that is not supposed to be there. For example, instead of the shining armor, the model predicted it as the and shining armor. Lastly, deletion is the omitted word. For example, instead of clear as night and day, the model predicted clear night and day. For generative models such as video or speech synthesis, we use mean opinion score or MOS as a measure of naturalness or realness of a synthesized signal. The score is assigned by a human evaluator in the scale of 1 to 5 as shown on this slide. It is very rare for people to assign perfect score, so scores in the range of 4.3 to 4.5 are usually considered excellent. Anything below 3.5 is considered unacceptable. In object detection, we want to correctly predict the object bounding box. In this case, we use intersection over union or IOU as a measure of performance of object detectors. IOU is also known as Jacquard index. On this slide, we illustrate the difference between intersection versus union for the case of evaluating A1 as the prediction and B0 as the ground truth. The max value of IOU is 1, while its minimum value is 0. Other performance measures used in object detection and classification are precision and recall, which are both defined on this slide. It is easy to interpret precision and recall from the perspective of credit card transactions. Precision is a relative measure of number of fraudulent transactions compared to legitimate ones. We want precision as close as possible to 1.0. This means only a very small number of fraudulent transactions went through, or we are keeping the bad guys out. Meanwhile, recall is a relative measure of legitimate transactions compared to misclassified as fraudulent ones. We also want the recall to be as close as possible to 1.0. This means all customer transactions are legitimate, or we are keeping as many good guys as our clients. Both precision and recall should be as high as possible. We want to minimize the number of fraudulent transactions, but not at the expense of discouraging good clients from using their credit cards. Related performance measures are average precision and F1 score. With experience, task, and performance now defined, how do we proceed with the actual machine learning process? A model learns by minimizing an objective function or a loss function. A loss function is a measure of how far is the model prediction from the ground truth. The smaller is the value of the loss function, the better. We minimize the value of loss function by tuning the model parameters using detrained samples. In deep learning, this is an iterative process performed using stochastic gradient descent, or SGD, or other forms of algorithms called optimizers. We can use an optimizer given the assumption that our detrained samples are IID, meaning they are independent and identically distributed. Independence allows to use empirical mean to compute loss. Identically distributed enables us to share the model parameters. We use empirical risk minimization as our basis of using a loss function for machine learning. ERM enables us to learn model parameters without the use of statistical models. In ERM, we can find a good set of model parameters by minimizing the distance between the observed ground truth label and the predicted label. Least squares loss, or MSE, or L2 distance, is one measure of distance that we can use to reduce empirical risk. There are other loss functions that we can use. In this table, we show common loss functions that we can use to train our models. Apart from MSE or L2, we have mean absolute error, or MAE, or L1. Cross entropy can also be used instead of MSE or MAE. In binary classification, we can also use binary cross entropy. The formula of each loss function for one data point is shown here. PyTorch supports all of these loss functions. Cross entropy has its origin in information theory. It is in fact a measure of distance between two probability distributions. Therefore, when we minimize CE, our model is closely approximating the true data distributions of our samples. This leads to correct model prediction. To illustrate, shown here are two-class distributions. P of X is the ground truth, while Q of X is the prediction. CE is equal to 0.29, meaning the model distribution Q is getting close to the true distribution P. To summarize, we use the experience detrained on a model to learn how to perform a certain task by minimizing a loss function. A measure of learning is through performance on the test. Thank you for listening.